Okay, so in this chapter, like I said, we started talking about electrochemistry, really redox reactions as well. Last time, I guess it would be last week. So a reminder that when we have a redox reaction, which is basically oxidation reduction reactions, those things usually occur together. So if something gets oxidized, that means that it probably lost electrons. And when it loses electrons, it will become more positive. And when something gets reduced, it has gained electrons, which means it will then obviously become more negative. So a number of times we use sort of just a basic number line and sort of following the trend as to sort of is it getting more positive, is it getting more negative, to figure out if it's reducing or going through oxidation. We also talked about oxidizing agent, and the oxidizing agent is again the substance that gets reduced, while the reducing agent is the substance that gets oxidized. Again, they're called sort of the opposites of that because they cause those effects in the other substance. So the reducing agent causes the reduction of somebody else and it gets oxidized, while the oxidizing agent causes the oxidation of something else, why it gets reduced in that sort of process. We talked about balancing redox reactions. And again, when you balance redox reactions, if it's just a simple reaction, you basically have your two half reactions, one being your oxidation half reaction, one being your reduction half reaction. And the important part is you always want to make sure that the electrons are the same in both half reactions before you add them together. Once you do that, you'll have your overall reaction. We also talked about balancing them in acidic and basic conditions. That's a little bit more complicated. There we use water to balance oxygen. We also add H pluses to balance out our hydrogens. Then we sort of add them together. We finished up last time, I think, getting into really sort of electrochemistry part of it, which is galvanic cells. And as we saw here in the previous slide, this is our, this is our basic sort of setup of a galvanic cell, one that you could build sort of in the laboratory. So your basic galvanic cell is usually set up such as this. Again, you can use two beakers. Inside those beakers are solutions that contain ions that are pretty much identical to the solid electrodes that are in there. So in this particular case, we have a solid zinc electrode. In the solution where the zinc is some zinc ions floating around. And same on the other side. Our other electrode there is a solid copper electrode on the right-hand side, and floating around in that solution is, again, some copper ions as well. And that's important because basically we're having a redox reaction happening here. And on the left-hand side in this galvanic cell, which is the anode, where we have the anode, that is where oxidation occurs. So as you see in the super zoomed picture on the left, basically our solid zinc will lose those electrons. As the solid zinc loses those electrons basically jump into solution and become ions. And the electrons then can travel along the wire, go through the voltage meter, which will give you some voltage, head to the other side or the other compartment. And on the other side, on this particular case, on the right-hand side is our cathode side. And on the cathode side, that's where reduction takes place. So all those electrons that are coming in will then add actually to the copper that's floating around in the solution on the bottom. And again, that copper 2 ions in this particular case will gain some of those electrons and then actually become more solid and come out of solution. There's also another important component, which is the salt bridge. The salt bridge is usually filled with some type of ionic compound, and it's really there to sort of balance out the charge on each side to keep that sort of potential difference between the anode and the cathode to allow those electrons to come towards the cathode side. Again, as we talked about, if you didn't have a salt bridge, because you're sort of dumping a lot of positive ions on the anode side, and you're actually removing a lot of positive ions on the cathode side, you would really get a buildup of charge on each side. And at some point, there wouldn't really be enough of a difference to allow those electrons to go from one side to the next. So the salt bridge sort of moderates that and moderates kind of the overall buildup of charge on each side, allowing it to have that proper difference to keep the electrons constantly sort of flowing from our anode side to our cathode side. Any questions on the galvanic cell there? So we finished up talking about the idea that, in these sort of problems that we will see, sometimes these things are kind of referred to in a few different ways. We sometimes talk about the cell voltage. We also talk about the EMF, or the electromotive force, and also sometimes the cell potential. In a lot of cases, there oftentimes in problems, if you're asked for any of those three things, you're sort of asked for the same thing, which is ultimately usually the cell voltage. So that's usually what you're kind of looking for. We can take an overall reaction like we have here on the screen we talked about, and write what is sometimes referred to as a cell diagram. So a cell diagram is sort of a shorthand of the redox reaction that's happening in a galvanic cell. And it usually always has a certain sort of pattern. And that pattern, as we talked about last time, is what we see here on the screen. On the left, we always start with our anode. And basically, it's sort of like a galvanic cell. So there's sort of two compartments in our cell diagram here. And one is related to the reactant side. One is related to the product side. So this part here, again, sort of our anode compartment. The first guy listed is a reactant. Second guy listed is a product. And as you can see here, reactant and product. Usually the ion will also a lot of times have the concentration written in there. Other things that we'll see along the way here are things like pressures, if we're dealing with gases, which can happen in this case. The two lines here represent basically the salt bridge, which is right there in that picture. And that salt bridge, again, basically separating our anode compartment from our cathode compartment. And in our cathode compartment, again, the first guy is our reactant, which is our copper 2. Second guy is our product, which is our solid copper. Also, again, here we do see the concentration given. So that's a really easy way to sort of remember it or do it. Just go reactant product, and that is usually how it basically goes. Again, you may see a couple other things, and we'll see it perhaps down along the road here, like pressures. They may even sometimes put a catalyst in there, not a catalyst, something like platinum or carbon or something like that, graphite, that's used as an electrode, but not really necessarily part of the reaction, and we'll see some of that as well. Any questions on any of that stuff there that we talked about sort of last time? Okay, so let's talk about sort of these electrochemical processes and these galvanic cells. So if we hook up a galvanic cell, as we see here in this picture, in this case, we have our zinc on one side, and on the right-hand side, we actually have a hydrogen electrode here. And since hydrogen is basically hydrogen gas, this is what I was talking about just a second ago. Here as the physical anode, or the physical cathode, is actually a platinum electrode. And again, that's sort of the solid representation of what is going on here. Again, because it's hydrogen gas, there's no real solid version of hydrogen. So sometimes something like platinum, like I said, something like graphite is sometimes used as sort of the physical electrode, in that case, some inert type of substance that's really not going to react or anything like that, other than be sort of a physical sort of electrode for this reaction to sort of occur. Here, the zinc again is going to be our anode. As we can see, the electrons are traveling away from it, which implies that it is our anode. And it's going to go to our cathode side here. And again, in this solution, we have hydrochloric acid. Hydrochloric acid is basically a source of H pluses floating around. Obviously, here we have sources of zinc ions floating around in the solution. And as those electrons come in, they're going to add to these H pluses, and we're going to make hydrogen gas in this particular case, hence the bubbles, if you can kind of see them here, being formed as a result of that reaction. So when we look at our cell diagram, we do see a couple of different things in there. So we have our anode compartment here, where our zinc is going from 0 in terms of its oxidation state to +2, becoming more positive with 2 electrons being given off. And again, if we want our overall reaction, this again would be a reactant. This would be a product. So, you know, you could almost kind of write it that way. Then we have our salt bridge here. And then we have our cathode side. And on our cathode side is the H plus going to the H2. So the H plus going from +1 to H2, which is 0. Again, if you draw that number line heading to the left, which is being reduced and going through reduction in this particular case. Now, we also do see a couple of different things here. Since H2 is a gas, we see a pressure included. And as I was talking about just a second ago, since there really is no hydrogen solid electrode, here we also see the platinum included here, again, as a physical electrode. Not really part of the reaction. You would still follow the same rules. So the first guy here would be the reactant, and this guy would be the product. So you would do a little H plus and H2 over there. Probably need a 2 happening there. And there's how you could get your overall reaction that we do see down here. So again, that's how you could kind of go from your cell diagram to your reaction. Again, you can see reactant product. Again here, the platinum, not really part of the reaction, just there physically to allow sort of that reaction to occur. Any questions on that? So that brings us to an important sort of aspect of electrochemistry here with galvanic cells. And that is something like the title says up there, which is known as the standard reduction potential. So let's talk about what that is. So the standard reduction potential, which is sometimes abbreviated as the SRP, is the voltage that's associated with a reduction reaction in an electrode when all the solutes are at standard conditions, so 1 molar and 1 atmosphere if we were talking about pressure. So, you know, how do we know, you know, what is sort of the values of everything else? Much like in a lot of parts of chemistry, they decided to sort of choose 1 electrode as sort of the standard. And it was a hydrogen electrode, and sometimes referred to as the SHE, the standard hydrogen electrode. The standard hydrogen electrode is this reaction right here, this half reaction. And they arbitrarily sort of gave it a value of 0 volts. So they basically gave it a value of 0 volts in this particular case, and pretty much used that value to determine what everybody else's values would be. So they hooked up things to the standard hydrogen electrode and basically figured out the values here. All right, hang on one sec here. All right, I'm not sure if you can still hear me. Can you still hear me? Feels like everything kind of froze on my side. You still hear me? You can still hear me? Yeah? Okay. Perfect. Okay. All right. So the standard Okay, give me one second. I'm going to restart kind of like everything's freezing on me right now, so I'll be right back in 5 minutes. I don't know if you'll be disconnected. If not, just reconnect. Give me about a couple of minutes here to Okay, so hopefully I'm back. Sorry about that. Everything just started freezing, so let's try this again. Hopefully it won't freeze again. All right, so as I was saying, and again, I think you heard me, but they did choose the hydrogen electrode as really the standard electrode. And again, they gave it a value of basically 0 volts, and they basically used it and created a whole bunch of different galvanic cells using hydrogen as one of the electrodes and basically measured the voltage. And from that, they're able to basically calculate all of the standard reduction potential values. And when we talk about standard reduction potential or SRP, it is for a specific type of half reaction, and it is what's in the name. It is a standard reduction potential, which means, as we can see here with our hydrogen half reaction, it is a reduction half reaction. So that reduction half reaction has our electrons over here on our reactant side. Again, that's the way that we can basically recognize it as a reduction reaction. So like I said, they took the standard hydrogen electrode and hooked it up with a wide variety of different types of electrodes. So here, if we look at this particular one here, we have our zinc here still acting as our anode, our hydrogen electrode acting as our cathode. And by measuring the voltage here of the cell, which in this particular case was 0.76 volts, they were able to determine the actual value of the zinc half reaction or reduction, again represented by this line as being minus 0.76 volts. And they were able to do that by using this equation here in the box. And this equation here in the box is an important equation And I'm going to tell you something about this equation right now, which might not make sense at this particular moment. Maybe it will, but it will later on when we start maybe doing some problems here. So one way that you could calculate the cell potential or the cell voltage is to take the E of the cathode minus E of the anode. And these are values that you can find in a table. So there's a table of SRP values that you can find. And remember that ultimately what we're talking about here are redox reactions. And these redox reactions, there's always an oxidation reaction, half reaction, and there's always a reduction, half reaction. Now, when we look up these values in this table, they are all written as reduction half reactions, which means in reality, one of the reactions are not written correctly, and that would be our anode here. Because an anode half reaction actually should be an oxidation half reaction, which means the electron should be on the product side. But you will not find any type of oxidation half reaction in this table, again, because it's a reduction potential table, so they're all reductions. So what that means is essentially one of the reactions that you find in that table, which is for the anode, in this particular case, actually the zinc one here, should technically be reversed. So although this is the reaction that we would find in the table, in reality, when we're using that reaction, we're actually using the reverse of it, which means the reaction that we're actually using in this particular case for our zinc is actually the zinc going to our zinc 2 plus our 2 electrons. Not really the reduction reaction that we would find in the table, which means actually the E of the cell for this reaction would be the opposite sign, positive 0.76 volts. So if we went to the table, we would find this value here for zinc. And when we use this reaction here, or this formula here, which is cathode minus anode, even though technically speaking, this is the correct reaction for this galvanic cell, this is actually the correct E value for this galvanic cell. If we choose to use this formula, we actually do want to use the value that we find in the table. And that is because this negative sign here, our minus sign, will actually change the sign for us. So if we were to put this into this table, this would be minus 0.76, which gives us positive 0.76 volts, which is really what the value should be. So there's two sort of versions of this formula that most people will use. Personally, I use this one most of the time. A lot of people use this one. So the rule is if you subtract, you should take the value you find in the table exactly how you find it. You shouldn't change the sign, because that's really what the subtract part of it is for. If you want to do everything to the letter correctly in terms of values and E values, you technically should change the sign of something like zinc. And if you change the sign, you should not subtract, but you should add. So there's sort of two versions of this equation. Easy way to remember it is if you're going to subtract, don't change the sign from the table. If you are going to change the sign, you need to add those two values together. Again, may not make a lot of sense or a heck of a lot of sense at this point. Maybe it does. But when we start doing some calculations, you'll see what I'm talking about. So just remember that sort of thing. If you decide to subtract, you should not change the sign that you find in the table, even though in reality the sign is actually changed for the anode because it's an oxidation reaction, not a reduction reaction. So they also, as you can see here, hooked up our standard hydrogen electrode to copper. And again, in this particular case, our standard hydrogen electrode is our anode, and our copper is our cathode. And what this also demonstrates is anything could technically be the anode or the cathode. So you potentially could make anything, either one. In certain cases, the galvanic cell will work okay. In other cases, it may not work so well. So using our E of the cell as our cathode minus our anode, again here, our hydrogen is our anode in this particular case. So that's going to give us 0 and tell us that the SRP value for copper is 0.34 volts. And again, the half reaction for that would be this guy here, would be the half reaction that goes with that value. So if you looked up copper 2 in that table, you would find this half reaction as written as a reduction, and you would find an SRP value for it of 0.34 volts. So again, anything can be used as a anode, anything can be used as a cathode. Doesn't necessarily mean that your galvanic cell will work really well. A positive voltage is really good for our galvanic cell. And again, if we look at our cell diagram, we again see our platinum here as our solid electrode, but this is again our reactant, our product, as you can see here, reactant and product. And coming this way across the salt bridge, which is right here, again, reactant and product. And again, you can see reactant and product. So again, that's sort of the formula there for our cell diagram. We see some pressure here because H2 is a gas. We also see some molarity here because H plus is a concentration. Same thing here with our copper 2. So there is a table of all these SRP values. Here's one. You also have one in your book that's very similar to this. And what you can see when you look at a table such as this is every single one of these have the electrons on the reactant side, which means all these are reduction half reactions, which is again why it's called a standard reduction potential. And basically all these are the cathode sort of reactions, if you will, that reduction reaction, which means when you go to this table to look up the value, like we talked about before, technically speaking, one of those guys should be reversed. And when we look at a table such as this, there are a couple important things about these SRP values that we should be aware of. First off, the SRP value is for the reaction as it is written, which means when you go to one of these tables, like I said before, they are all reduction half reactions. So that value that you find is specifically written for the reduction half reaction or for the reduction half reaction. So how do you know when you're given two things, you know, what is going to be my anode, what is going to be my cathode? Well, the way you're able to do that is, typically speaking, if you're not given any other piece of information, you're just simply given, hey, you made a galvanic cell out of these two things. The one that has the more positive SRP value has a greater tendency to be reduced. And if you think about the thing in a galvanic cell that gets reduced, that is your cathode. So if you're not given any other information other than, like I said, just simply you made a galvanic cell out of these two things, when you go to the table, the one that has the more positive SRP value should be your cathode, and by default, the other guy would be your anode. Now, if you are given some information, like you're given, you know, the reaction or something like that, or you're given in words how the reaction is taking place, you then should actually look at the equation and reaction and figure out what is being oxidized and what is being reduced. But again, if you're not given any of that information, you can simply go by the more positive guy. The half cell reactions are reversible. So as we talked about with our zinc reaction, again, the zinc written as its reduction half reaction has a E value of, I think it was minus 0.76 volts. Again, if we wanted our oxidation half reaction, we would reverse it. And again, what that does when we do reverse a reaction is we change the sign. So it goes from minus 0.76 to positive 0.76 when we reverse our reaction. So this is what I'm talking about. One of the reactions in all these galvanic cells technically should be reversed. So if you decide you want to reverse it and you want to actually change the value that you find in the table, then you should add those values together. Again, if you leave it, then you should leave the sign. You don't want to change it and subtract, otherwise you get the wrong answer. Lastly, something that's very common as well is, as we talked about, you do want to make sure that all of the electrons in each half reaction are actually the same numbers. So sometimes that does require you, as we've seen, to have to multiply a half reaction by a common number. And if you multiply a half reaction by the common number, so kind of like what we've seen with delta H and G and all those guys, typically speaking, you know, if we had to multiply everybody by 2, we typically would multiply something like the delta H by 2, delta G by 2, all that kind of stuff. We actually don't do that here. So if you need to multiply a half reaction to get the same number of electrons, you can do that, but it will have no effect on the actual E value that you find in the table. So you can multiply, for example, my zinc guy here by 40. You know, you can multiply 40, 80 and 40, and the E value will still remain the same. So it'll have no effect on the E value. It is not affected by having to multiply by a common number. Any questions on that there? All right, so why don't we try one here? So what is the standard EMF of the cell? Why don't we also write the balanced equation here and figure out our anode and our cathode. So what's our anode? What's our cathode? Write a balanced equation. Let's take a couple minutes, see what you come up with. Okay, so let's take a look here. So first thing, we're not given really any other piece of information other than these two half reactions. By the way, these two half reactions would be found in a table like we just saw, an SRP table. You would go and basically look these guys up. And when we do, again, as we talked about before, they're both written as reduction half reactions because these are SRP values. So we want to determine which one is our cathode, which one is our anode. So we do want to compare both of these values here. And in this particular case, the cadmium is a more positive value. So the more positive SRP, when you're not given any information about the reaction, will most likely be your cathode. So what we could determine from this is our cadmium would be our cathode, and this reaction here would be our anode by default. So what that really means is, technically speaking, this reaction for our chromium is not really written right. And technically speaking, we should reverse the reaction. So just to rewrite a couple of things here. Top one is perfectly fine the way it is. Bottom one really does need to be reversed, and we really should have chromium over here going to chromium 3 and 3 electrons. So what I was talking about earlier was I just reversed this reaction, which means technically speaking, the E value for the reaction I just written is actually positive 0.74 volts. So that technically should be reversed. The E value should become positive in this case. Now we could add these both together since we're looking for the overall reaction, but we really can't add them together right now because they are different numbers of electrons. So before we add them together, we do need to make sure we have the same number of electrons, and that is actually 6 in this case. So the top reaction does need to be multiplied by 3. Bottom reaction does need to be multiplied by 2 before we really can add those together. So rewriting it one more time here, 3 of our cadmiums with a +2 charge plus 6 electrons goes to 3 cadmiums with a solid there. And our E value here does not change, even though we multiplied by a common number of 3. It has no effect on the E value, which is something a little bit different than normal things we've seen. We're also going to distribute that 2 to the bottom guy, going to give us 2 chromiums. Goes to 2 of our chromiums with a +3 charge and 6 electrons. Again here, even though we multiplied by 2, it will have no effect on our E value. We are now actually ready to add these guys together. And when we add these guys together here, our electrons will cancel, which is what we're looking for to happen. And that gives us our overall reaction, which is 3 cadmiums reacting with a couple of chromiums, going to give us 3 cadmiums with no charge and no C apparently. So we got 3 cadmiums and 2 Cr3 pluses. So this would be our balanced equation that I asked you to write. We also have identified our cathode and our anode. So what is left is to figure out E of the cell. So again, I'm going to show you again the 2 options you have at this point. Since what I did here was change the sign, so since I changed the sign on this, I actually want to add both of these together. So E of the cell would actually be, in this case, minus 0.4 volts plus 0.74 volts. And that's going to give us 0.35 4 volts in this case, as our cell voltage. And again here, what you see is because I took the initiative and changed the sign, I added the values together. So that is definitely one way you can get E of the cell. You can also get E of the cell from that formula that we saw, which is E of the cell is E of the cathode minus E of the anode. So what we know is our cathode was our cadmium, which would be 0.404 volts, minus our anode here. And if we use the subtract, we're not going to change the sign, even though technically it is changed. And we're going to put in there minus 0.74 volts. And that's going to give me, as you can see, the same answer, 0.34 volts. So this is what I was talking about earlier. Some people want to do everything this way, which is perfectly fine, and change the sign of the anode. But if you do change the sign, you then need to add the values together. If you don't want to change the sign, that's actually okay too. If all you're looking for is what is the cell voltage, you can go directly with the values you find in the table, but you do need to subtract because the subtraction actually changes the sign for you. Now, one last really clarification again is if you were asked what is sort of the E value for this reaction here, the correct answer is positive 0.74. Again, remember that the E value is specific for how the reaction is written, just like up here, which is, this guy is written as a reduction, the E value that goes with it is minus 0.74. Any questions on any of those sort of steps or why we did anything there? Okay, so why don't you try another one here. A galvanic cell consists of magnesium and silver. What is the EMF? And why don't you also, we'll do the balanced equation here. And what is your anode and cathode? All right, take a couple minutes to see what you come up with in this particular case. Okay, so let's take a look here. So again, we want to take the same approach. We're not really given an overall reaction or anything like that. So we can definitely use our SRP values here to determine which one is going to be our cathode and our anode. Again here, when you do use the SRP values, you're looking for the one that is more positive, and the more positive one will be your will be your cathode. So in this particular case, that would tell us that we have our cathode here, that our silver is our cathode, and by default, obviously, our magnesium would be our anode. So if we wanted, again, just really the cell voltage, which is what it's asked here, you can simply go to the table just like you did there and find these values. You could go right into our cathode minus our anode. And since we were able to identify it, we could simply go right into it. And we're not going to change the sign here if we subtract. So I left the negative, and that's going to give me a cell voltage of 3.17 volts. Now, again, you could kind of take a different approach. And since I also asked for the balanced equation here, what that means is the magnesium here needs to be reversed. So we do need to reverse this guy. And if we were to write our balanced equation, our anode would be our magnesium, which again would technically be the reverse of the reaction that's found in the table. That also means that technically speaking, our E of this cell, our E for this guy would be positive 2.37 volts. Our cathode would remain the same, which would be 2 silvers going to 2 electrons and 2 silver solids in this case. Again here, we would also need to multiply this guy by 2 to get our electrons to be the same. So that's where the 2's came from. And again, by multiplying by 2, it will have no effect on the value of our E for that particular reaction. And again, if we add this together, we can now cancel out our electrons, which is what we want to do and why we needed to multiply by 2. Everybody on the left stays on the left-hand side of the arrow. Everybody on the right-hand side stays on the right-hand side of the arrow. And again, your other option would be to add these numbers together, since I already changed the signs. Again, if we add those values together, we do end up with obviously the same cell voltage as we got the other way. So you can see they both give you sort of the same answer. They both give you the right answer. Again, you know, if you want to do the minus, do not change the sign for the table. If you want to add them, you do need to change the sign for the anode one. Any questions on that particular one there? Okay, so then let's talk a little bit about the cell potential and some of our thermodynamic type properties like work and free energy, which is our delta G that we saw in the previous chapter. So work basically can be accomplished when electrons are basically sent out over a wire to do some type of work. So very similar to how batteries work. Again, if you look in a battery compartment, there's a little wire where the batteries go. Electrons, basically redox reaction happens. Electrons are basically transferred through the wire, through your device, and sort of powers your device and comes back to do that. So again, that potential difference, which is the voltage, is equal to a joule work over a coulomb of charge. That's what the C stands for. And ultimately what we see is that when a cell produces current, the cell potential is positive. So usually a positive value for cell voltage means the reaction is going to be sort of spontaneous. It's going to happen. A negative value, not so good for it. And really the maximum amount of work that you could do is equal to our delta G, which is our Gibbs free energy here. And tying that together with some of those equations that we saw before in the previous chapter, we do get a couple of equations here, or a few different ones, and we'll talk about these here in just a second. But the first important equation is the top one here. We have our delta G is equal to minus NFE of the cell. N is the number of moles of electrons, and that is the total electrons that have been moved from the anode to the cathode side. So what that means is, and for example, our previous example here, if we were looking for what N would be, there's 2 electrons here, there's 2 electrons here. The electrons here are the same electrons. These electrons that are being lost by the magnesium in this case are being gained by the silver in this case. So N here would equal 2 if we needed it. It would not equal 4. So you don't want to add those together. It would just be 2 in this case. Basically, whatever the number of electrons lost should be the same number that is gained, and that would be your N value in that particular case. F is Faraday's constant. That is this number right here. It's like 96,468, something like that. The real number, 96,500 is good. That's a joule over a volt over a mole. And a joule over a volt is the same as a coulomb, which is what that symbol is, a coulomb per mole. Now, if we look at our delta G that we saw from previous chapter there, we could also then set it equal to this, and we get another equation here that relates E of the cell to the equilibrium constant, Rk. And E of the cell here, by the way, E of the cell here is the one that we've been talking about. That is our cathode minus our anode. Again, in most cases, you would look up the values and calculate that, how we did on the previous couple of examples. R is our gas constant, and it is the one that involves energy. So 8.314 version here is what we're using. T is our temperature in Kelvin. N is our moles, F is our Faraday's constant, and K is obviously our equilibrium constant, products over reactants like we've seen many times. Now, if we happen to be at 25 degrees Celsius, a lot of these become sort of constants. And you basically can reduce this equation down to this guy. So if you're at 25 degrees Celsius and you kind of multiply everything on top and all that and divide, you end up with 0.0257 volts over N, natural log of K. Or if you're a more traditional log person, you could take 0.0592 volts over N, log of K. Or if you don't want to worry about these two equations, you could just worry about this equation here that's in the box and just put the numbers in, even if you're at 25 degrees Celsius. I will say that there might be a slight variance in terms of your answer depending on maybe which version of this equation that you choose and how you round. But usually a lot of times you'll get a number that it's an exponent. The exponent part will be fine, but the front part might be slightly off depending on how you round. So keep that in mind. If you choose a different version, you'll sometimes get a different number. So that brings us sort of our trifecta here that allows us to go from some of our thermodynamic properties to our electrochemistry properties by this trifecta here of wonderfulness. If we have our delta G, we could go to our E of the cell by this equation here, minus NFE. Or we could go delta G to K like we saw in the previous chapter, and obviously K to E using the one that we just saw here. So why do we say that if you get positive cell voltage, the reaction is going to be spontaneous? Well, if we look at really this equation right here, the number of moles is probably going to be a positive number. Faraday's constant is a positive number, which means if you end up with a E of the cell that is positive, your delta G will end up being negative. again, because of the negative that's here. And that would mean that if we have a negative delta G, the reaction is spontaneous, as we talked about. Now, if you get a negative cell voltage, the negative E and the negative side will turn our delta G into a positive number, which means the reaction is going to be non-spontaneous the way it's written. So that's why we say positive voltage means the reaction will be spontaneous, and we would expect, you know, as it's written, to head towards the product side. Any questions on that? So as I mentioned before, some of our normal stuff we just talked about, again, positive E should yield you a negative G. Negative G means that the reaction should be heading to the product side, which should give you a large value for K. Vice versa, if you have a negative E, going to give you a positive delta G, which means the reaction is non-spontaneous the way it's written, means it is going towards the reactant side, which means when you calculate the equilibrium constant, you should have more reactants than products, should yield you a small value of K. And if you're at 0, reactants and products are equally favored, as our delta G would end up being 0 as well. Any questions on that one? All right, then see what you come up with here. Calculate the delta G for the following reaction. And is it spontaneous? So see what you come up with. Okay, so let's take a look at this one here. So we're trying to calculate the delta G. Again, we're given some SRP values here. We're also given a reaction. So really nothing to do with sort of equilibrium constant or anything like that. So the only real one that we saw in terms of delta G that sort of involved our E of a cell, there is this guy here. I get it to do that. So we do want to find E of the cell. So again, our E of the cell going to be our E of the cathode minus E of the anode here. So when we look at the actual reaction, since it's given to us, our copper is going from +2 to 0, and our iron is going from 0 to +2. So again, our copper starting at +2, ending at 0, it is being reduced. So our copper, which is being reduced, would be our cathode. And by default, our other guy here should be our anode in this particular case. That means really here I could go right into here. Since I'm going to subtract, I could just take the values from the table, and that would give me 0.34 volts minus, which is going to change the sign for me, minus 44 volts here. That is going to give us 0.78 volts, which is what we need for this. Faraday's is a constant. That's that 96,500 number. And we do need to figure out N. So if we look at this, we can see that we do have the same number of electrons here in both. So N in this case would equal 2. F obviously equaling our 96,500 joules per volt per mole. And that means that we have everything that we need to go into here. Delta G would equal our minus 2 moles. Our F, which is 96,500 joules per volt per mole. And our E of our cell, which is 0.78 volts. Volts will cancel, moles will cancel, going to leave us with joules. Since we got a positive value there for our E of the cell, we would expect a negative value here for our delta G, and we do get a negative 150,540 joules, or if we kind of clean it up a little bit, maybe 150, or we'll go 150 kilojoules in this particular case. And again, these both would be negative. And it does make sense, again, if we look at it, we ended up with a positive voltage, which means the reaction should be spontaneous. We ended up with a negative delta G, which again should tell us that the reaction is spontaneous. So the answer would be yes, it is spontaneous. From either way, positive E of the cell or negative delta G. Any questions on that particular one there? All right, so give this one a go. Will nitric acid dissolve gold metal here to form gold 3 ions? Okay, so let's take a look here and kind of see. So we'll take our same sort of approach here, and we want to figure out what is our anode, what is our cathode. So in this particular case, you may look at our numbers here, and we do see that our gold is more positive than our nitric acid. And that may lead you to believe that the gold here is our cathode and our nitric acid is our anode. And if that's the case, you would be incorrect. So because of what it asks you, it essentially asks you, will nitric acid, which is HNO3, react with gold metal, which is solid gold, no charge, to form gold with a positive 3 charge? That means on our reactant side, we need nitric acid and solid gold. If we look at our half reactions, nitric acid, which is here, is on our reactant side, but this guy is on the wrong side. So we actually need to reverse the bottom reaction. And that would mean that actually here in this case, the gold is going to be our anode and our nitric acid is going to be our cathode. So remember that you really only want to use the one that's more positive if you're not given any information. So in this case, we weren't given the overall reaction, but we were given enough information in words, basically, that nitric acid needs to be on the reactant side and gold, solid gold, needs to also be on the reactant side. Any questions on that? So if we calculated our E of our cell here, taking our cathode minus our anode, our cathode in this case would be our nitric acid minus our anode, which is our gold, going to yield us minus 0.54 volts in this particular case. Now, because we did get a negative E of the cell, if we were to put that into our delta G equation, the negative here and the negative here would turn our delta G into a positive number. Both of those things tell us that this reaction will not occur, right? And that this is really a non-spontaneous reaction. And in fact, that's how they used to test gold. You know, you take it to a pawn shop or something like that, you add some nitric acid to it. If your gold's still there, it's probably real. If it's not there, then it probably was fake gold along the way. So again, really important to look at what they give you in terms of any information about the reaction so that you can choose the correct anode and cathode. If we were to sort of balance this guy out, again, the overall reaction would look something like this. This is our half reaction, which would remain the same. Again, our E would be 0.96 volts. We would flip around, like I mentioned, the gold here. And again, technically, you would flip the sign on that. When you would add this together, our electrons would cancel, leaving us with what the question really asks. If you take some gold metal and you react it with nitric acid, which is essentially these two guys together, you form gold 3 ions and some other stuff, NO, plus our waters here that would technically be there as well. And again, if you did change the sign, then you would also add these together and you'll get the same number. So if you decide to do it that way, E of the cell would be 0.96 volts plus a minus 1.5 volts, giving you your minus 0.54 volts as well. So again, a reminder that you can change the sign and add them or just subtract them. And as you can see, you do get the same answer regardless. Any questions on that particular one there? All right, so why don't you try this one here. I'm going to give you some values. Maybe it doesn't look like you have them. So our E of our SRP value for, let's do iron, is minus 0.44 volts. Our E value for silver here is positive 80 volts. All right, so let's see what you come up with. Here we're looking for the equilibrium constant for this following reaction. So see what you come up with. All right, so since we're getting to the end here, let's take a look on this. So this one, we're actually looking for the equilibrium constant. So we probably want to use the equation that involves that. So we saw E of the cell is equal to RT NF natural log of K. So that was the equation that we saw a little bit earlier there when we were looking at them. And we want to pretty much figure out all these things that we need. So if we look at a couple of things here, we have R, which is a constant. So that's that 8.314 number. Our temperature here does need to be converted into Kelvin, so that's 298. We do need to sort of figure out N, and F is also a constant, which is that 96,500 joules per volt per mole. When we look at this equation, we do see that the iron, it goes from +2 to 0, which means the iron is actually getting reduced in this case, and the silver is going from 0 to +1, which means it's getting oxidized. So again here, based on the equation that's given to us, the silver is going to be the anode, and the iron is going to be the cathode. So this again would not be a case where you would want to use these values. You actually want to use the equation given to you. So our oxidation would be our silver, and our reduction would be our iron, which means if we do our E of the cell here, going to be E of the cathode minus E of the anode. So since our cathode is the iron, it would be minus 0.44 volts minus our silver, which is 0.8, giving us an E of the cell of minus 1.24 volts in that particular case. So again, important, if they give you the overall reaction, you need to go look and see what's happening there. So now that we have E of the cell, we pretty much have everything we need. So E of the cell, again, going to be RT NF natural log of K. We are looking for K. So that's going to give us minus 1.24 volts is equal to R, 8.314. Our temperature of 298 Kelvin divided by our N, which is 2 moles. Again, we can see that from the half reactions here. And our F, which is our constant, 96,500 joules per volt per mole. And that's going to be the natural log of K. Cleaning up a bunch of stuff here. So if we clean up everything on the right-hand side, we got 8.314 times 298 divided by 2 divided by 96,500. That's going to give us something like minus 1.24 volts equals 0.012837 natural log of K. Dividing that to the other side, going to give us something like minus 96.59 is equal to the natural log of K. Again, by dividing this to the other side. At this point, we're going to take the E of both sides. I got the moles from the half reaction. So from the balanced half reaction here, we see it's 2 electrons. So that's where the moles come from the balanced half reaction. When you look up the silver half reaction, it'll just be silver plus 1 electron. Again, we need to make sure that the electrons are the same in each. So since the iron is gaining 2 electrons, the silver has to lose 2 electrons. And again, it's just the total amount that's lost. It's the same as gain. So N would be 2 here, not 4. Other questions on that? All right, so by taking the E of both sides, that is going to give us a K value of, call it 1.12. times 10 to the minus 42 as our K value. So we kind of want to see perhaps, does this perhaps make sense? So we did see that we got a negative value for our voltage. Negative value for our voltage means that we should also have a positive delta G. Both of those things should tell you that this reaction is non-spontaneous the way it's written, which basically means this reaction should be hanging out on the reactant side. And since it's hanging out on the reactant side, we should expect a small value of K, which that definitely is a small value of K. So again, it does make sense. Other thing would be, again, if you use one of the sort of shorthand versions of this equation, like 0.0257 over n, or the 0.0592 over n, log of K versus natural log K, you may again get a slightly different answer at the end depending on how you round it, but the minus 42 part should be right on. So you might get something like 1.23 depending on how you round it. Any questions on that particular one there?